Okay, so in this video, we're going to start talking about new growth models. These are not going to be linear. So the example we're talking about might be oversimplified and not numbers that make sense in real life, but just bear with me to follow along. And this is an oversimplification of how things work, but this is closer to reality. So let's say, suppose a bacteria culture in a lab doubles in size every hour. Okay, let's fill the table below to find out how much bacteria we have for the number over time. So the important thing here is that at time 0, okay, that's when you're starting, you have 10 bacteria. And so that 1 hour later, you have double that, so it's 20, right? Pretty simple. Then the next hour, you double what you had, and it becomes 40. So the next hour, you double what you had. It always doubles every hour, so now it's twice what you had, so now it's 80. And now it's twice the 80, and it's 160, and so on. So you get the idea, 640. So of course we're going to get to a formula for what's happening here. But let's keep it like that for a minute. Now we're going to change it slightly different. It's still increasing by percentage. Over here it's increasing by basically 100% every hour. And now we're saying it increases its size by 20% each day. So it's not doubling, it's not, but it is 20% more than what it had. So we know how this works if we work with percentages. So this entry right here, it's going to be the 10 bacteria that I had. You're going to multiply by 20%, right? Of course, you get a 2. But then you add it to the 10 that you had, right? The original 10. And let me write it over here. You add these, and you get 12, correct? So that's the correct way to do it. I'm going to keep it in one line. I'm going to show you what I want to do. So I'm going to write it like I had 10, and then I'm going to add 20% of it, right? And so I get 12. 10 plus 2 is 12, correct? Now the numbers are going to get like decimals, but we're going to continue in that fashion. And so my next number is going to be, I have 12. So I'm going to now, let me put this on the side over here. And I'm going to work with this one. So now my number is 12, right? I have 12 here. This entry is 12. So my new number is 12. And I'm going to have 12 plus 20% of 12, correct? That's going to be 12 plus 2.4, if I get this correct. So it's 14.4. Right, 20%, 10% of 12 is 1.2, so 20 is 2.4. It's 14.4. So that goes in here. So the numbers are going to get a little bit messy, but what I want you to see what happened here is I'm going to change the way I wrote this. This was a 10 plus 20% of 10. So I'm going to factor that 10 and write it like 1 plus 0.20. Right? If I do that in one step, I get to 12. Right? So if I did that, I get that 12. Now I can repeat that same idea here. If I say I have my 12, and it's 20% of 12. So if I factor the 12, I'm going to have 1 plus 20% of 12. Correct? So I'm thinking I multiply this times that, you get a 12, and then this times that, you get the second factor over here. Right? But now I think about this. This 12 that I have here really came from this 12 that I had here. So I can write it like this. That 12 is really like, I could copy this guy and paste it right here. Right? So I still have this other factor of 1 plus 0.20 again. But now, notice that what happens is that this factor is the same here and here. So I could have written it all like my original 10, and the factor 1 plus 20% or 0.20 squared. That's how I could have gotten in one step to 14.4. I did the math here. Let me do it in a calculator. This is going to be my calculator for this step. We're doing Desmo Scientific Calculator. You can download the app or look it online. It has an online site for it. So what I'm saying is that if you do 10 times, and the 1.1 plus 0.20, I can just write like 1.2, right? I can just do 1.2. I don't need the 0, right? 1.20 is the same as 1.2. Close the parentheses, and now I need a power. So the power is right here in this row. It's hard to tell me in that row. It's the second entry, right? But it's squared. But if you type if the first entry is squared, if you type the second entry, it has a to the b. Then you type the 2. Then it come in handy later. Okay. So that's what I got. So this is 14.4 that I got. So if you follow the steps so far, we're doing great, because now you understand what is it that I would need to do. Let me put this over here. Let me make all this work over here. Now I want to do it for 3. I could do the same thing again for my third step. I could say I'm adding 20% to 14.4. So I could say that's 14.4 times 1 plus 0.20. I'm skipping like to this step right here, right? But I can say then 14.4 is this 10 times 1.02 squared. So of course this number is going to go here. Is going to be nothing else but 10 times 1.2 to the third power. And so on. In general, I'm going to have 10 times 1.2 to the n power when n is 6, 5, 4, or 3. So I can do those very easily here. So I can just change that for my exponent for a 3, 17.28. For a 4, 20 point, I'm going to round to 7.4. For 5, 24.88. And for 6, 29.86. So the important thing here, of course, was to discover that this is my formula. Yeah, if you want to use function notation, it would be written like p parentheses n. And I wrote 1.2, but of course it came from 1 plus 0.2 to the power of n. And 10, this 10 right here, is my initial value, right? So that's what we're going to. This is called exponential growth. I have 2 ways of expressing it. As an implicit formula, this is saying the next step is 1 plus r, the previous population step. And that's what I was doing here when I said the next step, for example, we can grab in this one, this 14.4 is 1 plus 0.20, the last step, right, the 12. Or over here, the second step, the 12, was 1.2 times the first step. And just for last one, I could write here the next step, the 1728, is 1.2 times the previous step, the 14.4. So this is the first thing I can do, but then that doesn't give me a formula to find at any value in n unless I find all the previous ones. So the explicit formula is what I'm going to use mostly, and it's Pn 1 plus r to the n. The symbols here are P0 is going to be the initial value, right? When n is 0, remember that anything to the power of 0 gives you 1. So this quantity raised to the power of 0 gives you this one, right? That's the initial value. And just for sake of having this clear, if I say up here the r percent after a period of time, then it's 1 plus r, where r is this percent expressed as a decimal, right? So we say that the quantity p is having exponential growth, and the number r is called the growth rate.